Hello and welcome to the third lecture of the network security course. In this lecture, I'm going to talk about firewalls. Firewalls represent one of the most important tools in network security, so we dedicate this lecture to discussing firewalls and other devices that play similar role in network security. So with that being said, let's start. So these are the references that I'm using in this lecture. And what is a firewall? Okay, so firewalls have been around since the 90s or early 90s, and they're considered and probably still considered the primary defense mechanisms against network security threats. If I want to link firewalls to the previous lecture, which was about access controls, I consider firewalls as access control mechanisms. They represent uh, um, the checkpoints where packets have to go through, get inspected before they continue to a network. So in this case, we can we have to put the firewalls between any two networks that usually have two levels of security levels or risk levels, I should say. Traditionally, and I say traditionally because things change now, but traditionally the two networks that often require a firewall in between is the internet, which is the untrusted network. We don't know, it's a wild jungle out there, so we don't know what's in it. And the trusted network, which is the internal network. This view changed recently, so now we have the concept of the zero trust, which means that the network, even the internal network, is not trusted anymore. So we can expand the concept of firewalls by saying that the firewalls can be placed between any two networks that have two different risk levels. Um, and one thing before we continue in this lecture, I want to emphasize that when you go out there and buy a firewall, we usually buy something that has multiple functions, not just the function of packet filtering. We call these, or the market call them, unified threat management systems or next generation firewalls. And they are a box that has multiple tools. In this particular lecture, we're going to talk about just one function, which is packet filtering. Okay? So throughout this course, firewall refers to the device or the function that performs packet filtering, right? So just to distinguish between other functions like uh, intrusion detection systems, intrusion prevention systems, spam filters, all of these are important systems that we were going to discuss later, but the firewall in the context or within this course uh, is a packet filter. Right. All right. So as I mentioned, um, firewalls are positioned between networks that have different risk levels. And I say network, but it could be a subnet or a segment or a group of networks. We'll call them zones in general, right? So in this diagram here, we see examples of common zones in any network. So the first common zone is the private LAN, or usually the most trusted LAN. And then we have the internet, which is the totally untrusted, and we consider it the high risk. And then sometimes we have the demilitarized zone, which I'll dedicate some slides to discussing them. This is the zone where we need to put some assets, some servers, for example, but we need to allow access from the outside uh, to them to these servers. So there is a high risk usually with this in this zone. And then sometimes we have extranets, which is networks that are open for contractors, for partners, for consultants. They are not completely trusted as the private LAN. They are maybe more trusted than the DMZ because we know who is the user, we know who's accessing these networks. So there are multiple security zones. And by the end of this lecture, we're going to talk more about these zones. The idea here is I could put a firewall between any two zones. And the firewalls usually are positioned as in a choke point where think of a checkpoint, security checkpoint in the road. They're going to put it where most people, most cars will go through, right? So the firewall is supposed to interrupt the traffic flow, inspect the packets that's going through the path, the link, and decide whether the packet is supposed to be allowed to go or continue its path or dropped. So usually the actions is either allow or deny or drop, right? The terms are the terms used for actions can be different for different vendors. So sometimes it's allow and deny, sometimes it's permit or drop. So the terminology may be different, but the idea is either let it go or no, don't let it go. Firewalls, when we talk about firewalls, we should consider them as a function rather than a hardware device. So it can be a function, and the function can be either what we call a bump in the wire, so something that interrupts a link. And in this case, the firewall can be implemented as actual physical firewall. In the world of virtualization, it can be a virtual machine, but the idea is same either way. So the packet going through a link has to go through this checkpoint and needs to be inspected before it continues its way. Another form of a firewall can be installed in a host, and I think in the previous slide there was a mention of hosts here. It can be installed in a host itself, and in this case the firewall function as a bump in the stack. The stack means the TCP/IP stack. So the packet will come to the host, and rather than continue the stack from the physical layer upwards, it has to go through a firewall function where it's getting inspected, and if it's allowed, then it will continue up the stack. If it's not, then it will be dropped and it will never continue. So in this case, the firewall is implemented as a piece of software in the host itself. The host firewall will protect just the host and try to make sure that nothing gets, or no malicious software, malicious packets will find its way to the host. Everybody familiar with this form of firewall? Probably your desktop or your laptop has a firewall built in, and you can also have a firewall installed just to add another layer of protection. Firewalls usually considered the first victim of attack, and if they are compromised, let's say if there is a denial of service attack targeted toward the network, the first device that they will encounter usually is the firewall. So if the firewall is compromised, the firewall tends to disconnect the connection to the network. So we call this defaulting to an open open connection. So that means that you cannot reach the network anymore, right? So default to open or default to close. If you default to open circuit or open connection, this means that, well, if the firewall fails, there will be no way for the packets to continue its way to the network. That's usually preferred to the opposite, which is open um, or unfiltered connection, which let everybody go. Right. Some devices we see them that when they fail, they default to allowing all traffic to go through. Right, which is not good. Okay. So let's talk about the primary functions of a firewall. So the original firewalls were considered simple packet filters. The the firewall looks at the content of the content of the header of the packet. Usually, the header, the IP version, the layer three the layer three header contains the IP addresses, source and destination. Source and if you go further to the layer 4, you will see the the destination source and destination ports and so on, right? So most of the filtering happens at layer 3, sometimes at layer 4, and the packet filter will look at the addresses and sometimes the ports and decides whether this packet is allowed or not. So it's simple filtering that depends on the IP header. These kind of packet filters are considered static packet filters. The function is always the same. Um, they look at layer 3 elements or layer 4 elements, and they decide whether the packet goes or not. Well, in this case, the issue is with the static filtering is that it doesn't look at the context of the packet, right? So let me give you an example. If a client establishes a TCP connection with a server, right? TCP connections um, contains a lot of packets that have to go through the same path. In this case, the static packet filter will look at each packet, inspect it as if it has nothing to do with other packets. So it will go through the same process for every packet, which is time consuming, introduces delay, and more importantly, it doesn't look at the context. It see each packet as an individual unit that it doesn't have anything to do with other packets, and it performs the same function of checking the packets every time. Um, and another problem with this is that um, again back to the client server example, when you send packets from the client to the server, you are expecting traffic to come back, a reply, right? So a packet filter will not see or will treat the reply as different set of packets. So if you are trying to create rules for packet filtering, you have to create rules for both directions, for the direction of for packets going from the client to the server and from server to the client. So there are two rules for the same type of traffic. Another issue with packet filtering is that it looks at the header only and it doesn't look at the payload. Okay, which means that if traffic has or carrying malicious software, well, it doesn't really, the packet filter doesn't do anything about that. It just passes it through based on the header information. Advantages: it is fast, it is transparent to the host. The host will never see the firewall. They establish connection to the destination, and the firewall will just be completely transparent to the host unless packets are dropped. So the host will notice that traffic is not going through if the firewall start dropping packets. Um, The other weaknesses of static packet filtering is that when the filter looks at each packet individually, and I mentioned this already, if you are, let's say the sequence of packets is carrying a virus, the static packet filter, it doesn't recognize the virus because the virus may be included in multiple packets, not just one. So looking at one individual packet at a time, the virus will not be apparent, right? Will not be clear. Another weakness is that let's have the example of segmentation, packet segmentation. So the filter may look at the first packet and look at the header and the content of the header, which is the IP addresses, and the TCP header, which has the port numbers, and it may decide that, okay, I'm gonna drop this packet because this traffic is not allowed. The segments, the fragments, I should say, the later fragments, they don't contain the TCP header. They contain only payload. So subsequent fragments that belong to the same original packet will be allowed because they don't contain any TCP header, so they will be allowed. This is one of the ways for denial of service attack to happen, actually, by sending fragmented packets, and the first packet may be dropped, but the subsequent fragments will be allowed because simply the packet filter will not recognize them, or will not recognize them as a threat. All right, so the next generation of filters or firewalls, they started think about all of these weaknesses and find solutions for them. So we get something called stateful inspection and dynamic packet filtering. If you think about the previous slide, now we have solutions. Instead of looking at each packet individually, we now look at packets as a part of a session. And now the word state comes from having the state of, or refers to the communication sessions in this case. So if I want to explain this maybe in a diagram, I'll say let's look at the situation where we have a client and a server. As you know, TCP sessions start by sending SYN and then SYN, the three-way handshaker, and acknowledge. So the firewall, if it's sitting here in the middle, the firewall will look at these packets and keep track of the session, recognizes, okay, there is a new session between this client and this server. So let's keep track of this session. So now we are tracking, or we're tracking the state of this session. So the state, the initial state is, okay, the session started. Let's look at the packets. The packets have the information in the header. So we have the IP addresses, source and destination. We have the TCP ports, the destination TCP port, the source TCP port. So we have all the information that we can keep track of. If this session is allowed, then the subsequent packets that belongs to the same session, they don't need to be inspected again. They are allowed, so we don't need to inspect them. because they belong to the same session. And this session keeps, or the firewall keeps tracking of the uh, session until finally the session is terminated. So that's what we mean by stateful inspection. The other benefit of this type of firewall is that if the firewall rule says that the traffic from the client to the server is allowed, then the implied rule is also the reply is allowed as well. So we don't have to have two rules, one going one direction and the other one going the opposite direction. We just need to have one rule that says traffic between these two nodes is allowed. So that simplifies the rules a lot. Okay, so this is the idea behind stateful inspection in summary. Stateful inspection can typically goes for information in layer 3 and 4, but it can also go up to the application layer. One issue with this type of filtering is that what about traffic that doesn't have a session? TCP has a session, start and end, very clear. But what about UDP? It doesn't have the concept of a session. Traffic like ICMP doesn't have a concept of session. So how the filter recognizes these? So in this case, the filter will create a kind of fake session or a dummy session for this. If the filter, we'll go back to our diagram. If the filter recognizes that there is a UDP traffic going from the server or from two nodes, so in this case we have the firewall again and the traffic going UDP here. UDP still has the IP addresses, still has the UDP port number. So this information and others can be kept in a table, right, that has session number and information about the session. Right? So these can go, and the filter can keep track of them. So if you are sending traffic to UDP 161 from the client to the server, the reply from source port UDP 161 to the client, it will be recognized as part of the session as well, right? So in this case, the firewall can still treat UDP traffic as a session and will keep track of it. The only problem here is with TCP, we have a clear start and clear end of a session. We have the SYN and the three-way handshake at the beginning, and then the FIN and the acknowledgement at the end. So we know the start of the end of the sessions. In UDP, the start and the end of the sessions are simulated by timers. So the UDP traffic goes between the two nodes, back and forth, after, or maybe in one direction, doesn't have to have a reply, because UDP can also maybe a thermostat is sending temperature to a server. The server never replies, just receives the UDP packet with the information, and that's it. But still, the firewall can create a session, and it inspects the first packets, create a session, and then any related packets will be treated the same. After a while, there is a timeout. If the firewall doesn't see the packets between these two nodes for a certain time, it will terminate the session. So it will clear the session, and now the session is over. If the same client sends UDP again to the server, it will be inspected again, and it will be the firewall will create a new session for that. So the sessions are created and terminated based on timers. Same thing with ICMP. You send an echo reply. There is an exchange of echo and echo reply between two nodes. The firewall recognizes this as a session. It will keep track of the session until there is no packets for a certain time. Then it will terminate the session, and so on. Okay, so the stateful inspection and dynamic packet filtering has an advantage. Um, Packets not necessarily inspected continuously, so they are inspected maybe only once at the start of the session. It can go a little bit deeper than just the layer 3 inspection. It can go further than that, up the layers, and it can recognize a packet as part of a session, right? Which means that it will recognize, for example, that if the TCP packets is out of sequence, so TCP sessions packets are sent in a sequence, so it can recognize a packet that's out of sequence that may drop it or consider it as not part of a session, so it doesn't allow it. So it has an advantage over the static filtering. Now, the risks involved with stateful inspection and dynamic packet filtering is that attacker may attempt to fool the firewall into thinking that the packet is part of a session by manipulating the header, right? So changing the content of the header so that it can pass as part of a session while it's not. Right? So these are some of the risks. Another function common to firewalls is the NAT. NAT is not by itself any type of filtering. It was considered as a way to reduce the need for public IP version 4 addresses. So instead of having every node out there equipped with a public IP address, instead of that, we can have local network devices assigned private IP addresses, and then when they go outside with a public IP. The assignment of the public IP happen at the router, or in this case at the firewall. So the firewall takes the local IP address and convert it to public IP address. Sometimes the assignment is static, so every private IP address is allocated a public IP address, a smaller pool, but still statically assigned. And the common thing that we see nowadays is the port address translation, or PAT, or sometimes we call it address overload, where all the private IP addresses are assigned the same public IP address, a single public IP address that goes outside. The firewall in this case differentiate between different devices inside by assigning port numbers. So it uses port number to differentiate between one host and another in the inside network, in the internal network. I'm not going to go deep into network address translation. I'm assuming that this has been discussed in another course. The only thing that I want to mention here is that network address translation has benefit to security, which is hiding the internal structure of the local network. So if the outsider sees all traffic coming from one IP address, which is the public one, it doesn't really know the details of the internal network. It doesn't know what the IP addresses in the internal network is. It doesn't know how many addresses out there, how many nodes out there. It doesn't see anything. Okay? So actually, for a long time, NAT was used as the only security measures in networking. organizations will just put a router and NAT everything, and that will be enough. Now, of course, that is considered a weak security measures nowadays, and you're not supposed to rely on NAT as the only security measure. But it still has benefit of hiding the details of the local network. Okay, so firewalls work mainly at layer 3, layer 4. If they look at the sessions, they need to know the sessions, so they need to look at the information in layer 4, the transport layer. But if we go deeper than that, if we go to the application, we get a form of firewall, we call it application proxy. So the application proxy concept is can be explained this way. So let's use a diagram here. So let's consider this scenario where we have the client and server. Just move the server a little bit further here, and we have this middle device, which is the proxy. So in a TCP session, the traffic will go as usual, starts by the three-way handshake. In this case, the client cannot reach the server directly, so it has to communicate with the proxy first. The proxy recognizes the session, right? So if the session is allowed, based on the parameters, the content of the header and so on, the proxy will establish its own session with the server. So now we have two sessions, the session that's going from the client to the proxy, and another session that goes from the proxy to the server. All other traffic has to go through the proxy and has to be inspected before it's allowed in both directions. So the proxy here looks at not just the layer 3 and layer 4 information, but it can look even at the content, the payload, right? So up to the application layer. The proxy can be a specific proxy that's only for email, so it looks at the email, it looks at the content of the email. It could be a proxy for web servers, it looks at the content of the HTTP. So it could be a specific proxy for a specific application. And the job of the proxy is to monitor the content mainly of the traffic and allow it. So proxy can be used here to maybe prevent leaking of sensitive information, for example, by looking at the content, the payload itself. All right, so let's look at it acts as the middleman, specific to various applications. It can inspect application-specific elements like the IP address, domain names, etc. They perform deep packet inspection. When we see the term deep packet inspection, means that we are looking at up to the payload, right? So it's not just the header. The difference between the proxies, or one of the differences between the proxy and the firewall, is the proxy is not transparent, right? The proxy is well seen by the clients. So firewalls normally they are transparent. Clients do not need to know there is a firewall on the network at all. They just see traffic going from the client to the server without any. So the firewall is totally transparent to them, unless packets are dropped, as I said, right? But in the case of proxy, the client has to establish a connection with the proxy. They cannot go to the server exactly. So how is that done in practice? In practice, the web browser, your web browser and your laptop, instead of it has to be configured to go to a proxy. So manually or sometimes using automated tools, every client, every web browser in the local network has to be configured so that it can go to the proxy first, right? So, which means that it is not transparent. All right, so why do we do that? We do it because we want to either protect the clients or to protect the server. So the proxies can be let's say this is a network. We have a local network here. We have a local network here with a firewall, and the firewall connects to the internet. Uh, and we have another firewall and servers. Here are the clients, right? So the proxy can be implemented as part of the firewall or a separate firewall, a separate device here or here or both, right? If we put it here in the client side, this serves as a protection for the clients. So the clients, they have never uh, contact the servers directly. They're always, the servers here, they're always contacting the proxy. So there is never a session between any server and client. And that protects the clients, right? Sometimes we want to protect the servers, so we want the proxy on this side, on the server side. Again, in this case, no clients can talk to servers directly, so all the sessions are between the servers and the proxy here, and the clients talk to the proxy on the other side. Okay, so one of the benefits of this scenario is that if there is an attempt for denial of service attack, whether it's um, the two types that I mentioned in the previous lecture. There is the SYN attack, where the client start a session but never completes it, so it sends a SYN, the first SYN, and then doesn't send an acknowledgement in the third packet of the three-way handshake, so the session still remains open or not complete, so the server become busy and it doesn't do anything. It cannot handle any more sessions. So the proxy in this case will prevent this type of attack, right? Because it recognizes that there are sessions that are not completed yet, so the server will never be affected. The proxy will be affected. Also, if there is a traffic huge amount of traffic going to the proxy is the one that's going to be interrupted rather than the server. So the proxy will take the brunt of the attack and will handle the attack rather than the server itself. So there are benefits of using proxies. Um, Now, by the nature of the proxy, every packet has to be rebuilt, right? So the traffic here, when the packet that goes from the client to the proxy, it has to be recreated again by the proxy, right? Um, at least the information in the header have to be changed, so the server at the right side here, it doesn't see the source address of the client, it will see the source address of the proxy. So packets need to be rebuilt before it continues, and they are rebuilt in both ways. All right, so this is another explanation of what I just said. So the workstation starts by sending traffic to the proxy here, proxy firewall. Step one. Step two, the session is established, so it replies. So the green is the session established. The green and red are the packets that needs to establish a session between the workstation and the proxy, and then there is another traffic between the proxy and the server. So it's the same diagram that I mentioned. Okay, proxies are um, introducing delay. They introduce delay because they have to recreate the packet every time. They have to do inspection, so they introduce delay. So as a way of avoiding this, we can have circuit proxy. The circuit proxy is different from the application. The full proxy is in the way that it operates. So again, to explain the difference, let's assume that here is the proxy again in the middle. We have the three-way handshake. So the proxy job is to handle the three-way handshake only. And then if the packet is allowed, or if the session is permitted here, the remaining traffic will go directly without passing through the proxy. Right? So the circuit proxy works only at the start of the session. Right? So that's the main difference between, or the main function of the circuit proxy. Now, once the firewall can start inspecting the packets beyond layer 4, we can do a lot of things. We can do content filtering because now we see beyond the header, we see the payload, whether it's a proxy or not, we can still do other things. So let me talk about the proxy first. So if we have a proxy, we can do something that uh, firewalls cannot do. Right? So a firewall like this one, let's forget proxy for a minute, and just regular firewalls. In a regular firewall that looks at the header information, and by regular firewall I mean either static or stateful inspection firewalls. Right? So the traffic goes from the client to the server, and it has to pass through the firewall. The firewall will inspect the header and let it go, and the same thing vice versa. Right? So the traffic can come back from the server to the client, so it goes and inspected in the firewall. Um, f- Traffic nowadays, if you're visiting a website, you are using HTTP. Right? But now it's very common to use HTTPS, which is secured using SSL or TLC, TLS protocol, which means that the traffic is encrypted. So with encrypted traffic, the firewall cannot see the content. That's a good thing and bad thing at the same time. So encrypted traffic introduces privacy, protects privacy of traffic and all of this. So if it passes through the internet here, nobody can sniff the traffic and see what's inside, right? But it also poses a risk in security because encrypted traffic, any content is encrypted, including malicious software, including sensitive information that can pass without being detected. So a client can leak sensitive information about organization to the outside through HTTPS without the firewall seeing it or without anybody seeing it because it's encrypted. Same thing, a malicious actor outside can send malicious software to the inside encrypted, and the firewall or any other device will not see it. So HTTPS started to create problems for security people. The solution for that is actually proxies. So how is that is a solution? Let's consider the full proxy here, which inspect everything. So because HTTPS works end to end, the client will start creating a session between it and the proxy, and this is HTTPS. All right, the proxy has to decrypt because it's the endpoint here for this session. So it can decrypt all the packets coming to it from the client, look at them, and then establish another encrypted session, another HTTPS session from the proxy to the server. So now what happens is traffic goes encrypted from the client to the proxy decrypted, look at the content. If it's okay, it creates another encrypted session from it to the server and so on. Right? So that will continue, and this is a solution for to prevent uh, any malicious traffic to go undetected because of the encryption. Right? So proxy is a good solution for this kind of threat. So everything still goes encrypted to the internet, but at the proxy, the traffic is decrypted, inspected, and it's allowed to go if it's okay. Content filtering goes beyond, or it's not just limited to being to proxy. We can let the firewall go into the payload and look at, for example, the content. If you are going to a specific URL, specific domain name or specific URL, that URL, it will be included in the payload. If the firewall can look at the payload, detect the URL, and either deny or allow the packet to go based on the content, then we can introduce content filtering. We can say the firewall will not allow you to go to a suspicious or blacklisted website, so it allows you only to go to a website that's allowed by the organization, or sometimes it blocks the users from going to social media websites. Like you cannot go to Instagram, you cannot go to Facebook, right? Based on based on the URL, or you cannot play a game based on the TCP port or the application content in the packet. So in this case, we can go beyond stateful inspection. We do also content filtering. Okay, so where to put the firewalls? In the interest of this course, we always look at these devices, their function. So we need to understand the function of all these security measures. Firewall is the one that we're talking about now, but we're going to talk about others later. So we always need to know what is the function, and also importantly, or equally importantly, is where to place them in the network. Because it's not just enough to understand the function of the firewall, but where to put it. I already mentioned that we put it in the choke points or in the boundaries between different security zones or different zones of different risks levels. So again, part of this slide talks about guidelines. So where to put the firewalls? Usually we put them where there are two networks that are clearly divided, or they have two distinct functions, and then we put a firewall in between them. The simple example is we have a wireless network connected to a wired network. Both networks are clearly different. That they are different by technology, one wireless and one wired. Also, they are different, or they are distinct in terms of risks. Wireless network usually they have a higher risk than wired because we really don't control who access them. The access is, well, we do control, but what I mean is the signal, the wireless signal propagates in a different way than the wired. The wired signal, the wired network, we have ports, and unless somebody goes and plug in into a specific port, they don't have access to the network. While in wireless, the propagation of the signal can go beyond the building, so somebody who's sitting outside the building can have access to this, or can reach or can receive the signal, so they can have um, a way to hack into the network. We'll talk about wireless security later, but for now, one of the ideal positions for firewalls is to put them between the two networks, between the wireless and the wired, as an added security measure. Another example I mentioned earlier is a demilitarized zone, or DMZ. The DMZ traditionally used to host servers that needs to be accessed from the outside. So a typical place for a firewall is to put it in front of the DMZ so that it inspects all the traffic coming from the outside and make sure that only traffic going to specific servers is allowed. In general, we need to put firewalls whenever we expect hackers to coming from, right? And that's, let me give you another example, practical example. So let's assume that we have a network that spans a, uh, a large area. Um, well, let's assume we have a network that has cameras. And the cameras are distributed in a wide space, outside, outdoors. And we have also a subnet that holds or carries desktops or laptops. So this is where employees are connected. These two subnets are distinct in their in their security. These probably the employees, they have desktops that probably vetted by the IT department. We know what the applications are, so we know the employees. The employees are treated or trained to on security measures. So we trust this network. This network, however, the outside network is the access. The cameras are outdoors. They are accessible by anybody at night. Somebody can go into simply replace them with a device. So take out the camera and replace it with a laptop and start hacking. So these two networks are naturally have a different security levels. So one of the things that we can do is to have a firewall that separates the two, so that we, for example, we don't allow the traffic from this network to go anywhere but a particular server, maybe a server that is designed to store all the videos from the security cameras, but the traffic is not allowed anywhere else. So to mitigate or reduce the risk. Right? So this is what I mean by having different security zones and different security levels or different risk levels. The final point that I want to make here is that uh, firewalls are expensive devices. They introduce delay. They introduce they add delay to the traffic. They introduce choke points in the network. So it's not like, okay, let's be safe and put firewall everywhere. No, the idea is you put firewall where there is a legitimate risk and there is a significant risk that that justifies the extra expense and the extra effort that you're going to put. So the final point here is says conduct a risk assessment before deploying firewalls to ensure practicality, cost effectiveness, and optimal security. So these are always in the security. There's always weighing the expense, and the risk. If the risk is low, you're not gonna put ten thousands of dollars for a firewall just to like where there's no significant risk involved, right? So you always have to um, weigh your options, basically. Okay, so we talked about packet filtering and we talked about a lot of things, but we didn't really mention how we implement these. So we implement them by putting rules. We commonly know them as access control lists or ACLs. Rules, um, we there are different structures of the rules. Almost every vendor has a different way to define these rules. So we're going to talk about a generic way to define the rules. But before that, we're just going to go over two main philosophies of the rules. The first philosophy is deny by default or imply deny and allow by exception. This means that if I don't put a specific rule to allow traffic, the traffic is denied by default. Right? So I have to go to the firewall and put specifically the traffic or the rules that for the traffic that I want to allow. So if I want to allow traffic to go for port 80, I have to go and say traffic port is or that contains port 80 is allowed. By default, traffic that goes to port 81 is denied because I didn't put a specific rule to allow it. So that's one philosophy. The other philosophy is the opposite, which is the implicit allow, right, or implicit permit. So allow by default, deny by exception. So the only everything is allowed unless I specifically say denied. Nowadays, you can have the firewalls always follow the first philosophy, always follow the deny by default, allow by exception, and this is the recommended. This is the way you do it, right? Some firewalls, some switches, they have access lists that can work either way. So you can do allow by default, deny by exception. There are certain reasons to do the latter, to do the second one, but the common firewalls will by default do the deny, implicit deny. And for the rest of this course, it is highly recommended. It is actually probably mandatory to use the deny by default approach. So unless otherwise stated clearly, we always assume that we are using the deny by default approach. Okay, so how do I determine the rules? Firewall rules cannot be decided just by the IT people or by the security people. It has to implement the organization policy. In the previous lecture about access controls, we said that authorization is determined by organization, right? And this is no different. So the rules, who decides whether this traffic has to go to Facebook or not, or whether traffic to Google can go or not. So that's determined by the organization. It's not by the security people. Obviously, there are common recommendations by the security, but usually we follow the organization's policy. So to start, you have to understand what the business requirements are, what are the essential business processes. Do employees need to access this website or that website? Do they need to send emails do they need to access this particular application outside? So you inventory all the things that employees need to do, and not just for the internet, also locally. For example, I go back to this example. Do employees here need to access all the cameras, or just maybe the security guards? Maybe just a subset of employees need to access the security camera. So why everybody is allowed? So we need to design a policy so that only the security guards, only certain hosts in the network are allowed to access the cameras. So we look at the organization's policy to do that. We determined the protocols, ports, and IP addresses that we need to handle. So now we are going down to more details. Probably the business people will specify the general ideas or the general policies. Only security guards can access the security cameras, but then it's up to the technical people to determine what does that mean in terms of technical details. What are the ports? What are the applications? What are the IP addresses? And then translate all of this into actual rules, actual access lists. And generally speaking, we cannot just go to the production network and make changes. We have to maybe try it in a simulator or try it in a prototype network, make sure that everything works perfectly before we go and implement it in production. Many organizations have a change management process where before you make any change to the production network, you have to go through a process where you apply for the change, justify your change, and go through a process where there is an approval. And then after that approval, you are allowed to make the change. Right? So you have to go through this if the organization is following these procedures. And finally, everything has to be documented. So these are the rules, the general rules for making any changes to the firewall rules. Okay, some of the common firewall rules that maybe you will find them in any network, and these are just examples. Anything from the inside, it usually allowed to the outside. Inbound responses are usually allowed. So if the internal user is accessing a website, the traffic back is allowed as well as part of a session, right? All access to the firewall from the outside is blocked. You cannot allow somebody from the outside to access the firewall or even ping it sometimes. So you block that. Um, Email traffic, it has to be sometimes initiated from the inside, and sometimes it has to be initiated from the outside. Email comes from the outside as well. So sometimes you need to allow it. As I said, sometimes the email servers have to be put in a DMZ so that we have an extra protection. ICMP traffic, sometimes it's blocked so that nobody can ping from the outside to the inside. Telnet is considered to be insecure, so we need to block it unless somehow we need it. But usually and this is not just the Telnet, any protocol that is not being used, it should be blocked, right? And you don't have to block specifically if you use the deny by default approach. So the deny by default means that anything that you're not using is denied by default. So this line is needed only if you are using the second approach, which is the allow by default. Um, so, as I said, generally we follow the implied deny rule, which is unless something specifically allowed, we deny it. Okay, let's look at the rules. As I said, multiple vendors have multiple ways to express the firewall rules, but we're going to look at the generic rules that we will use throughout this course, right? So, because we are looking at packet filters, which look at the headers, we need to specify the header elements. We need to specify the elements for filtering. So most rules will have at least 5 or 6 elements. The protocol itself, so this is how the firewall try to distinguish between TCP versus UDP versus ICMP, or generically IP. Right? The source address, the IP version 4 or IP version 6 address, the source port. This is less important, I'll explain why, but also part of the 6 elements. The target IP address and the target port, which usually specify the application, and the action, which is either allow or deny, permit. Sometimes we use this different permit, drop, different keywords, but the idea is either allow or not allow the packet. Vendors sometimes they add more details, so flags, for example. So if I want to specify not just the TCP but the TCP SYN packet, so I need to specify flags. So some uh, some some vendors will allow to specify the flags. Direction, whether it's inbound or outbound, also another option, and sometimes the actual interface. These add more detail to the rule elements, but we will focus only on the top 6 or top 5 rules in this case. Okay, let's see these rules in action here. So in the left side of this slide, we have several types of traffic going on. So traffic 1 and 2 refers to packets going from the client to somewhere in the internet, maybe a web server, and then there is a return traffic, so traffic 1 and 2. Traffic uh, 3 here is traffic that initiated from the outside and coming into the internal network. Traffic number 4 and 5, traffic initiated from the outside, coming to a web server and a email server. So our rules here to the right says that traffic going from host 192.168.16.0, any traffic from actually this network, not just the host, but this network, is and the source port can be any, the address can be any, and the port is the target port is 80. This traffic is allowed. What does that mean? It means that, and by the way, the protocol is TCP. So this means that any HTTP traffic is allowed from the inside to the outside, right? So TCP port 80 means HTTP port, and this basically allows internal host to access any website. Okay. Rule number 2 is the mirror image, so it's the same protocol. The source is any, the port is 80, and the target is 192.168.16.0/24, and the target port is any, also allowed. This practically allows the return traffic. This, if you notice, these two assumes that the filter is a static packet filter, which means that I have to allow the traffic from both sides, right, from both directions. In stateful inspection and dynamic packet filtering, port or rule number 2 is not needed, right? It's already implied that if I establish traffic from the inside to the outside, any return traffic will be allowed as well. Actually, if you think about it, this rule is dangerous because it allows anybody to initiate. Number two, I mean, rule number two is dangerous by itself because it allows any people from the outside to initiate traffic to the inside without any limitations. So this is just for illustrations, but normally it doesn't happen in practice. Right? Rule number three says any traffic from the outside is denied. Right? So any traffic from from the actually this one is to the firewall. So the firewall is we assume that the firewall has public IP address 10.10.10.10. So we are not allowing any traffic that comes the to the to the firewall itself. We are denying it. Firewall rule number four allows any traffic to go to a specific server and specific port. Server .20 here and port 25. And the final one, rule number five, allows traffic to come to this particular server and this particular port 80. Now, I'm not going to comment on how good this rule is. There are many problems with these rule sets, so don't take it as a good example. Just the purpose of this as to illustrate the 6 elements, and we see here the first element is the protocol, and then the second element is the source IP address. The third element is the source port, and the target IP address, the target port, and the action. This is the main purpose of this slide. So don't take this as a good example of a firewall rule. This is actually not a good example at all. But I need to illustrate the 6 elements and how they are arranged. One thing I want to mention as a comment, you see here that we use any. This means that any address or any port, right? And in most cases, when traffic is initiated from one host to another, TCP or UDP specifies the target port, while the source port is usually a random number for in a particular range. So there is no good reason to specify the source port. There is no good reason to specify the source port. Here we have this port is this in rule number 2. We see that we are specifying the port only because we know that, or we want to say that traffic coming from port 80 HTTP is allowed. Practically, there is no good reason to specify the source port. So most of the time we will just ignore the source port. All right, we'll visit this topic later. All right. If you look at this table here, this rule set, packets when they come, they follow a specific flowchart, a specific sequence. So the packet comes and the firewall will start matching the first rule first. So it try to compare the packet header content with these 6 elements, and if it matches, the action will be taken, which is allow. If it doesn't match, it will go to the second rule, and so on until there is either a match, or if it doesn't match anything, the implied rule is the packet will be dropped. So we will call this the first match apply rule. And this is how all firewalls work. So we start by we check the packet against rule I. I can be 0, 1, 2, 3. We check it against rule I. If there is a match, then the action will be taken. So the packet is either allowed or denied. If it's allowed, we'll pass the packet to the next port. or the next process of the firewall. Maybe we need to route it, so we push it to the next process, right? Not not necessarily directly to a port, but to the next process. If the action is denied, then we drop the packet. All right. If we go back to the match, if there is no match, we go to the rule number I plus one and so on. Right? This means that the order of the rules is very significant. And that actually what we will discuss in more details. The rules or the sequence of the rules is very significant when we design the rule set for firewalls. Okay, because of the importance of ordering, we need to arrange our rules so that the more specific are the first, so and the more generic are come next. So what I mean by that is if I want to if I have a specific rule that says traffic from let's say TCP traffic from IP address 192.168.16.1 and port any and going to 10.0.0.1 port 80 allow. Okay, so that's specific rule because we specified the port, we specified the source, we specified the target. So we made a lot of specific. So let's say a more general rule that says any IP traffic from network 192.168.16.0/24 port any going to network 0/24 also port any denied, right? So this is the least or the least specific because we don't specify an IP address. It's more this one is a network rather than a specific host. So if you look at compare the two, you will see that this is less specific than the top one. The second one is less specific than the top one. So the order here is significant. We put the more specific first. Right? And maybe this is one example, but we can also have other examples for more specific versus less specific rules. Generally, we want to have the more specific rules come first. Also, if some rules are used more, or we know that some rules are matched more often, then we want them to be at the top. Why? Because if we have lots of rules, and sometimes the firewalls have thousands of rules, literally thousands. Right? So if we have rules 1, 2, 3, and so on, let's say one of these rules allow traffic from the outside to go to an internal web server, right? So because we expect a lot of people to visit the web server of the organization. So we want this rule to be near the top. If we put it near the bottom here, what will happen is that any packet will come and doesn't match. It will be compared to a lot of rules and it doesn't match any of them until it reaches the rule at the bottom here. So what does that mean? It means that the packet will be processed multiple times before it gets to the rule that it matches, which means more delay, right? So now disregarding any optimization that the firewall vendor will use. Maybe they will use parallel processing, maybe they will use specialized integrated circuits. We'll just ignore that for a minute and just assume that packets are matched one by one from the top to the bottom. Well, in this case, well, it will take a long time just to reach the bottom. So if I know that this rule is matched a lot, we'll just push it to the top so that it will be processed faster. Okay. Um, so that's the rule related to more common traffic should be placed earlier. Again, fewer rules are better. Right? The more rules, the more confusion, the more processing time, and the more likelihood for misconfiguration and problems that we will discuss later. So we want to have firewalls that have fewer rules. So if money is not an issue, two small firewalls with two different functions are better than big firewall with a lot of rules in it, right? And always use the universal deny implicit deny rule, right? So that's assumed to be the last, right? Another thing that we need to do is sometimes we need to monitor the firewall rules and how they are matched or accessed, right? So, and for many purposes, one purpose is monitoring, another purpose is to keeping track, accountability. Remember, we talked about accountability in the previous lecture. So we want to make sure that our rule design is good by monitoring. So every time a packet matches a rule, we want to log the match, which means that a log entry will go to a log file that says this firewall has been matched at this time. Maybe there's a timestamp or there's other detail uh, that includes the content of the packet that matched as well. So we can add log options to some of these rules or all of them. Firewalls sometimes they have a counter, also a counter that counts how many packets matched these rules. All right, the useful for these or the use for these fields or extra options is that we keep track of the usage of the firewalls. So if a packet is being denied and we log that packet, we know why it was denied. And if this happens more often, we recognize a threat. So let's say there is an implied deny at the end. Right? The implied deny can be logged as well. So a packet comes and matched with all of these rules, and then finally it matches the implied deny, and it is dropped. But being dropped is transparent. Nobody sees the packet when it's dropped. But if it's logged, then we can keep track of why it's being denied. If I see a lot of packets coming from a specific source and it is always denied, I know that there is an attempt of hacking, and I may actually go and create an entry here, another rule at the top that says traffic from this particular source is denied. So this means that I can make the rules more efficient rather than allow packet to go through all of these matches and deny it at the end. I deny it early. Also, I can, by using the counter, I can see which actually rules being matched a lot and which rules are not are rarely matched. It could indicate that my design of the rules has a problem. It's lack of performance, right? Or the performance is not as good as supposed to be. So I see maybe some rules are being matched a lot while other rules are not matched too much. This means that maybe this rule is not being useful, right? So if it's not being useful, why it's there? It could be just a mistake in the design, and maybe remove it or modify it somehow. So logging and keeping track of the matches is useful. People tend to log everything. That's not good because logging creates a lot of delay by itself. Every time a packet is logged, there are millions of packets coming in a matter of a very short time. If you going to log everything, that's an overhead, that's a lot of processing and a lot of storage as well, and it's not very useful. Sometimes too much information is not going to be useful, so you have to be careful about what to log and what not to log. So maybe initially when the rule set is designed, you want to log many packets just to make sure that the design is correct, and then maybe you can remove some of the logs here and just keep track of things that um, that you want specific information about, right? So rather than log everything. Syslog is usually the protocol of choice when we use logging. Most firewalls will send the logs using syslog to an outside server that keeps track of or saves all of these logs. Sometimes the firewall itself can store these logs. Now, storing in a local storage of the firewall may be problematic because no firewall has unlimited storage, so there's always limited storage, and you buy the storage at premium. It's more expensive, so maybe you want to direct the logs to some outside server. Okay, so at this point, we want to look at some inconsistencies. We'll call them anomalies in firewall rules. The anomalies usually happen when we make a mistake in the ordering of the rules. So we're gonna take a look at certain common mistakes or common inconsistencies in the rule. Okay, so the firewall rules anomaly result usually when we make a mistake in the order. So there are reasons for these mistakes. Um, if sometimes we put a rule in a way that is never being matched, never being reached, right? Sometimes we create rules that are similar, so they do the same job. Um, Sometimes we make rules that are inconsistent or confusing a little bit. So we are going to go over these rules, and we'll call them anomalies or inconsistencies. Most of this information coming from one particular set of papers published by a group of researchers. So this is the source, and if you look at the references at the top of this recording, you will see the source, the actual papers, and you can read them. Um, they are really useful in recognizing the common inconsistencies that we can find in the firewall rules. All right, but I will use this example from the same source to discuss these inconsistencies, and this actually doubles as a good way to put an example for a complete set of firewall rules. So you'll see here we have a network that has um, uh, two subnets, 140, 192.37.0, and another one, 161.120.33.0. So these are two subnets. There is a firewall and there's the internet. If you go through these rules, there are 12 rules. You notice that they have the 6 elements, even though the port, usually the source port, as I mentioned, there's really not good reason, not many good reasons to specify the source port. So there most of the time it's any here. The protocol is specified as TCP in the first rule, and the address, the source is 140.190.37.20. The destination is stars here. Stars is, in this course, we just replace it with any. It means the same thing. It's either asterisk or 0000 or any. All three ways represent the same thing, which is any, right? Destination port is 80 and the action is denied. So if you look at this rule, right, just this rule, and try to understand what it means. It means that if, first of all, 140.192.37.20, this is a specific port, a specific host in this network, in network D1, right? So this line, this rule says that any traffic from any TCP traffic from this particular host going to port 80 is denied. All right. So in English, this particular host cannot send TCP traffic anywhere. As soon as the traffic hits the firewall, it will be denied, regardless of the destination. Okay. Then the second rule here says traffic from 140.192.37 dot asterisk, which is, you can also replace it with probably the better way to do this is to write it this way. The network is 137. I forgot what the network is, but let's assume this. So this is equivalent to these two are equivalent. This is actually what you find in a real firewall. This one is just an example. So this is real, this is not, right? So you won't, I don't think there is a firewall that has, you can specify the address this way. So this is the better way to specify address representing a network. So throughout this course, we will follow this convention rather than this one. Okay, but just for the sake of the example, because I took a screenshot of this example, so we're going to use it as is without any modification. So anyways, so this rule says any host from this network 140.192.37 can go the accept here, so can go to any port 80, any address with port 80. So HTTP is allowed anywhere, right? If you compare these two rules, you see that this particular host, which happens to be in the same network D1, is not allowed to go, is denied, is not allowed to use TCP port anywhere, TCP port 80 anywhere, while the rest of the hosts are allowed, right? Okay, moving down, the rule number 3 says any host, any network going to this particular host 161.120.33.40 using port 80 is accepted. So what does that mean? Notice that 161.120.33 belongs to D2. So this means that any host in the internet can come to this particular host in D2 with port 80. Also, 140 can send traffic to 161. So because it's any here, so any host anywhere can reach 161, 120, 33, 40 with TCP port 80, right? So that's accept. And if you go down, each rule has a meaning like this, and you can see here we changed UDP. So UDP is allowed through port 53, which is DNS, I believe. So from 140 to 161, from anywhere in D1 to this particular host in D2 with this particular target port 53 is accepted. So at the end, you can see here there is an implicit, not implicit, but explicit deny. So any TCP traffic from any host going to any host is denied. And here UDP traffic from any host or any network to any host or any network is denied as well. So in this particular example, we have explicit deny, not implicit deny. What is the difference if we don't mention this, right? So if rule 8 is not mentioned and rule 12 is not mentioned, then it's up to the router. If the router usually the router or the firewall assume implied deny, right? So these 8 and 12 probably not needed. But anyway, as I said, we'll just follow this example. Okay, so the first problem and the most dangerous problem is the shadowing problem or shadowing anomaly. What shadowing anomaly means? The conditions are stated here in mathematical ways. So we'll always, just to simplify the explanation, we'll always assume that there are two rules. One is called Rx and one is called Ry. Rx is always higher than comes first before Ry. So all of these conditions will use the same kind of convention. So we have Rx, the order of Rx is less than the order of Ry, which means that Rx comes before Ry in the rule set, and Rx is that has exact match as Ry, but the actions are different. Or Rx comes before Ry, and Ry is inclusive match, which means that Rx is a subset of Ry, and the actions are different. In this case, we have a shadowing problem. All right, so the example here from the previous set is rule 4 is shadowed by rule 3. So let's look at it in plain English and it will be easier to understand. So rule 3 and 4, one of them is shadowing the other. Okay, so what does that mean? Look at rule 3. Rule 3 says that any host source host here going to 161, 120, 33, 40 will be accepted, would be allowed. The traffic from any network, not just any host, any network going to 161, 120, 33, 40, the traffic would be accepted. Then rule 40 says that this particular network 140, 192, 37 going to this particular host is denied. Okay? If a packet comes with this 140, 192, 137 as a source IP address, it will match 3 first, right? Because 3 is, and as I said, it's inclusive match here. So, in other words, Rule 3 is a superset of Rule 4. Rule 4 is a subset of Rule 3. So a host coming from 140, 192.37 dot, let's assume dot 2, it will match this, it will match the any, right? And it will be accepted. So shadowing means that this rule, rule number 4, will never be reached. Because every packet comes, it will match 3, it will be accepted, and it will never match 4, and it will never be denied. As I said, this is one of the most dangerous problems because we have two different actions. We want to accept certain packets and deny other packets, but because of this shadowing problem, we are actually accepting all of them. We're not denying anything. Rule number 4 is never reached. And so in this shadowing problem, you have to focus on two things. The first one is the action must be different. If the action is the same, well, that's a different story, and we'll talk about this in the next slides. But the first problem, or the first thing we need to notice is the action is not the same. One accept and one deny. It can be deny accept or accept deny, doesn't matter, but the action is not the same, right? The second thing is the top rule is a superset of the bottom rule. If that happens, if there is a condition like that, we call it shadowing condition because the bottom rule will never be reached. Right? The two rules don't have to be adjacent, right? So in this particular case, the two rules are adjacent, but one rule can be rule number 3, the other rule can be rule number 9, so they are far apart. So they don't have to be adjacent. So the shadowing rule is still shadowing rule whether they are adjacent or not. All right, so that's the shadowing anomaly. So this is considered an error. It can be fixed easily by reversing the order. So if I go back and reverse the order, so TCP 140, etc., this rule number 4, if I push it at the top, now everything works fine, right? Because now we exclude this particular network, so deny it first, and then we allow everything else. So, and that matches what I mentioned earlier by putting the more specific rule at the top. So the more specific rule in this case is rule number 4. We put it at the top, so the order is good. This particular network will be denied first, and then everything else will be allowed. Okay. The second rule is called correlation anomaly. The correlation anomaly happens when we have an overlap, when we have instead of one rule is a subset of another, we have actually an overlap in between them. So you see here that the conditions are the actions have to be different, right? And there is a correlation relationship between them. And here the example is rule number 1 is in correlation with rule number 3. So let's look at this example and then I'll give you more examples. So you see here rule number 1 has a specific IP address. Rule number 3 has any. So the specific IP address is a subset of any, right? Any includes everything, while this is more specific. So this is a subset. Rule number 1 is a subset of rule number 3 in the source IP address. When you look at the destination, it's the reverse. The target or the destination IP address of rule number 1 is any, while it is more specific in rule number 3. So we call this correlation. One rule is a subset of another rule in one element, while it's a superset in another element, and both actions are different. So I want to explain what is the dangers behind this. This is not considered always an error, but it's a danger. So in order to do this, I'm gonna copy uh, this set and explain what is the impact in the notes. So let's go to the notes. Here are the same rule here, and let's look more specifically at these two. So rule number 1 and rule number 3. So let's look at the meaning of both rules in just plain English. So the first rule says that if traffic comes from a host in the bottom network here, D1, and if it needs to go anywhere with port 80, it will be denied. I'm just gonna use different colors here just to make things clear. So this means that traffic going to the internet with port 80 or traffic going here with port 80, both of them will be denied. Right? So that's rule number 1. Rule number 3 says that any traffic going from anywhere, TCP traffic coming from anywhere to this particular host here will be accepted. Let's use different color for this one just to make sure that's clear. So traffic coming from the outside, coming to this one, and also if it's coming from here to this one, both are okay, are allowed. Alright, now let's consider the scenario where we have traffic from this particular host, the red one, going to the green one. Okay, so I'll just use another color here. So there is traffic going from this particular host, the red to the green. This packet will be denied. Why? Because it will match the first rule. The first rule says you cannot go anywhere, right? So you'll be denied. Okay, let's reverse these two. Let's put this packet, this rule number 3 at the top, right? So I'm just gonna write it at the top and say, so this rule will be TCP any, I'll just use the asterisk here, port any 161, 120, 33, 40, right, port 80, accept. In this case, a packet, the blue packet again, going from the red host to the green host, will go to this port, this rule, the first rule. It will be allowed, right? It will be allowed because this rule says any source going to this particular destination using port 80 will be accepted. So it will be allowed. So the point here is, because of this correlation, the order of the rules, it changed the meaning. In the original order, traffic coming from the red host to the green host will not be allowed. If I change the order, it will be allowed. Okay, so what does that mean? It means that you have to be careful. This may not be a wrong thing. So correlation may not automatically means that there is a problem or there is an error. So we consider that a warning. Be careful, because if you flip the order, you will get a different meaning. In the original order, uh, the red host was not allowed to go to the green host using port 80. When I flipped the order, it was allowed. So, and this is what the correlation means. So if we go back to the correlation anomaly, you'll see that the correlation anomaly is considered a warning, and usually means that maybe we didn't state the rule in a good way. Maybe we can specify it more or specify it better. And the solution is to just look at the order and see if we want to change the order, or if we want to leave it as is. So that's the second anomaly we have. The third anomaly is called generalization, and I don't really like to name it anomaly, because it's actually a very common way to do the rules, and it's a very good way as well. So I don't know why it's being specified as anomaly, but I'm gonna just continue following the source or the reference naming convention and just call it anomaly as well. So what is generalization? Again, the actions have to be different, right? And rule X is coming before rule Y in the order, but in this case, rule X is a subset of rule Y. So if you look at rule 2 is generalization of rule 1. So if we go back, or maybe we'll go back to just the slides here. Right. So you'll see here that rule 1 is a subset of rule 2. Right? This is a particular host. Rule 1 is a particular host, while rule 2 specifies the entire subnet. So this particular host is not allowed to go anywhere with TCP port 80, so it's denied, and the rest of the network can go with port 80. So this is not a mistake. This is not an error. Actually, it's a very common way to do things. I may need to um, restrict some host from doing certain things and allow the rest of the network to do things. So I may also do the opposite. I may say this host 140 190.37.20 can accept here, the action is accept, so I can allow a specific host to go to a network while denying the rest of the network. So generalization is not an error, it's actually a common way to do things. I'll give you another example that I mentioned earlier when I mentioned let's say this example here, where I said this particular host at the bottom is allowed to go to any network at the top there, what did I say? I said these are cameras, right? So let's write this rule quickly. So I have multiple hosts. One of them is allowed to access the cameras while the others are not allowed, right? So we'll call this network, we'll give it a short IP address just for convenience. So this is network 10.0.0.0/24, and this is network 20.0.0.0/24, and this particular host is, let's call it .10. So in this case, the rules, if I want to allow this green host to access all of the cameras while preventing the rest from accessing the cameras, what I do is I'll write rule number 1. Let's assume it's UDP. I'm just going to pick any protocol UDP. Source is 20.0.0.0. Actually, because it's a host, so I'm going to specify the others. 10. Any as a port, source port, any. The destination IP address is 10.0.0.0/24, and the port, let's call it 161, and the action is allow or permit. Right. And the second rule will be UDP 20.0.0.0/24, any, and 10.0.0.0/24. I could say also any here, allow, deny. What does that mean? It means that first, this is very specific, so any UDP traffic coming from this particular host going to this particular network on this particular UDP port is allowed. The rest is not. The rest of the network, the rest of the hosts here are not allowed, right? So any other device going to this destination, any UDP traffic is denied. I can even go further and say any here, so not just any UDP traffic, but any traffic at all. So this is generalization rule, right? Generalization, which means that number 2 is generalization of number 1. And this is the common way to do it. So this is not an anomaly, and we don't consider it an anomaly. We consider it here is not considered an error if it's an intentional for a specific rule to make an exception of the general rule, right? And so that's what we mean. So all of these rules that we talked about, or the anomalies, the shadowing, the correlation, and the generalization, they all have something common, which is the actions are different. Now, the last anomaly here, or the fourth anomaly, the action is the same. Or redundancy means that we have the 2 rules or more than 2 rules doing the same thing, right? So because they are doing the same thing, they're just occupying space in the rule set, and they are not being useful. The 1 rule will be sufficient, so why are we doing 2? Right. So if we have, so in mathematics here, x is in the order of rule x is less than the order of rule y, and the actions are the same, but rule x is what is it called? Exclusive match. EM, sorry, I forgot what EM is. Exact match, sorry, exact match. So it's either exact match or inclusive match. Exact match means are x exactly doing the same or having the same elements as rule y. Inclusive match means the rule y is actually superset of rule x. Right? Either way, we have a redundancy. So rule 7 is redundant to rule 6, and rule 9 is redundant to rule 10. So let's look at 6 and 7, 9 and 10. 6 and 7, right? So the two actions are the same, except in both cases, right? Rule 6 is superset of rule 7 because we have the source addresses are the same. Destination address any includes also the more specific host. So if I remove this one, the second one, there would be no need, there will be no effect, right? So I can remove the 7 one, the number 7 here, and there will be no effect because the packet going to this address 161 120 33 40 will match rule number 6 anyways, and it will be accepted anyways, right? The opposite is not true, however. If I remove number 6, well, then 161 will be accepted, but what about other destinations? So you have to be careful here. So they are redundant, but 7 is the one that we need to remove, not 6, right? Uh, Again, another example is 9 and 10. 9 and 10, this is the opposite. The destination match, the actions match, the port also matches. Be careful, by the way, the match has to be an exact match for everything, not just the addresses, right? So here, 10 is a superset of 9. So packet 140 coming from 140, 192, 37 is going to be accepted. And if I remove number 9, they're still going to be accepted anyways by rule 10. So number 9 here is redundant, right? So the 9 is redundant in this case, and in the case of the 6 and 7, the 7 is redundant. So the one that I should remove is 7, and the one I should remove is 9, right? So in other words, I'll keep the superset. Okay, so this is considered an error. Why? Because we just increased the size of the rules list without actually adding any more benefits, and the solution is to remove remove the redundant one. We have something called irrelevance anomaly. Irrelevance anomaly is a rule that doesn't do anything. It has no benefit whatsoever, right? So in this case, rule 11 is irrelevant because the traffic that goes between the source and destination does not pass through this firewall. Right? So let's go to rule 11 and see what it does. So rule number 11 says that traffic from 140, 192, 38, any host here, going to 161, 120, 35 is accepted. But notice here that it's hard to recognize it at first, but this is 38. We don't have a network 38 here. And the destination is 35. We don't have 35 here. We have 33. So this rule has no benefit to the firewall at all. We don't have these two networks. So if I remove number 11, there will be no effect whatsoever, right? And it's just occupying space here for no reason. Notice, by the way, since speaking about redundancies, right? So let's take a look at as there are other redundancies, by the way. Maybe okay, so let's skip that and talk about it in some other time. But there are other redundancies and there are other anomalies in the same set. Okay, There are other problems or other inconsistencies or anomalies in the rule sets that don't fall within those five that I mentioned. So, in general, the use of any too much is, we call it excessively permissive rules. So if you create a lot of any rules, especially accept rules, right? So any accept, that's too permissive, and that means that allows a lot of traffic to go without being checked, right? So you have to make sure that you don't have a lot of any in your any's in your rule set. Another problem is the disabled rules. So why we create disabled rules anyways? So sometimes administrators wants to check something. So I create a rule and then I go and disable it. You can, so it means that the firewall does not consider it when it matches packets. All right, that's fine for testing purposes. But if you have a lot of these disabled rules, then they will consume memory of the firewall and they won't have uh, any useful purpose. So you should eliminate them as much as possible. So these are the other rules that you find, um, and you have to eliminate. So this is an illustration of all the rules that we discussed. Notice here that three of the common anomalies have opposite actions, while one has same action. And there are the ones that we don't really specify the action, so too permissive, um, or disabled or irrelevant, can have any actions, it doesn't matter. So this is a way to differentiate. Sometimes you get confused between redundancies and generalizations, right? But redundancy, they have the same action. They have the same action, rule X and rule Y. They can be exact match, or one is a subset of the other. So you just remove the subset because it depends on the order, by the way. But you just remove the subset, and nothing will happen. Um, in the shadowing, correlation, and generalization, the actions are opposite. One is allow, the other one is deny, right? And we have to be careful. The shadowing is considered an error, so you never allow shadowing in the rule set, um, because the packet always matches the first rule and it will never go to the second rule. Warning for the correlation, because if we change the rule, if we change the order of the rule, the behavior change. So we have to be careful that the two rules are in the correct order. And generalization is typically good thing, not a bad thing. Is actually, it's not a bad thing. This is a common way to make rules specific for specific ports or specific hosts. So that's not really a bad thing. You just need to make sure that we are doing the right order, right? We're putting the more specific rule at the top. So in this case, we match rule X before we match rule Y. So rule X will take effect before rule Y. Okay, so that's just a depiction of all the anomalies. Now, at the beginning of this lecture, I talked about firewalls being at the boundaries between different zones of different security level or risk level. So we're going to talk about security zones next, and I'm going to follow the recommendations of the Canadian Centre for Cybersecurity about defining zones. These are publications that are available and you can look at them And they are updated, so we'll make sure that we have the latest update all the time. All right, so it's common practice and best practice for networks to be segmented into subnets or into different physically or logically. So you can segment them physically by allocating different switches to different parts of the network. So in the camera example, you may have a separate switches that connects the outdoor cameras, and they are totally different and separated from the switches that are connecting to local desktops and servers. Okay, so that's physical segmentation, and you put a firewall in between. It can also be logical, so you can have a VLAN um, that separates traffic from accounting department versus engineering department, for example. So you can have a segmentation. Um, a security zone will be a logical grouping of devices that have the same risk level. Okay, I can give you multiple examples, but just will go on now. Um, if I segment, one of the reasons for segmenting the network, first of all, there is design benefits of this, but from the security point of view, if I put all the security cameras in one subnet, and I know that this network has a special type of traffic, special level of security versus servers, for example. So I can treat the traffic in this network in a special way, right? Also, if there is any breach, if there is any attack, hacking to security cameras, I will prevent it from being propagated to other parts, right? Um, in terms of compliance, usually that reduce sometimes in certain standards, we want to make sure that we are compliant with let's say health regulations, health security regulations, or a credit card security compliance. So if we put all the health servers and the health information and health databases in one segment, I can limit my compliance to that particular segment instead of trying to have the entire network compliant with the regulations. So this will be clearer in future lectures, but that's one of the benefits of just splitting the network into multiple segments. Okay, so if each one of these segments is called the zone will have a well-defined perimeter. It has also strict boundary. So if I let me exaggerate a little bit and say, if these two networks are connected and they are the same subnet, and there is no point of calling this a zone versus this is a zone, because they are in the same segment and they're not separated by anything. So the zone has to be first. It has to define. It has to have a well-defined perimeter boundary. Right? So this means that I have to separate the two by maybe a router or a firewall, something. Right? So this will be a separate zone, and this will be a separate zone, and there is a clear boundary in between. Right? Also, the systems have to be similar, or they have to be similar. They are susceptible to similar type of security threats. What I mean by that, again, if I go to this example, if I create, this is a subnet with a camera, outdoor camera, and a server, right? And then I have a router here, and I have another set of cameras, outdoor cameras, and a server here. There is no point of calling this two different zones because they have the same characteristics. They have, if they are outdoor, well, they are susceptible to the same risks. If they are carrying the same type of, the servers will be susceptible to the same level of risk. So zoning here doesn't mean a lot because we have two different zones with the same characteristics. So what is the point? We may as well call them one zone, right? Even though they are separated physically, but they are, from the security perspective, they are the same zone, right? So the zones have to have these three common things. They have well-defined perimeter boundary. They have strict boundary protection. Not just we have a router in between and the traffic can go back and forth. No, it has to have a protection. We have to have a limitation. Otherwise, there is no meaning for, that boundary has no meaning. And a third one is they have to have the same level of risk or same type of threats. So if we follow these three rules, then each zone will have a different security requirements. The security cameras will have different security requirements than the servers, than the desktops, than others. Each zone has a discrete points of entry defined by firewalls and possibly by other controls. Firewalls is the topic of the discussion today, but we will see later there are other controls like IDS, intrusion detection systems, for example. So these are different devices, but we may need at least a firewall or a packet filter when we mention firewalls. The other thing is only required traffic can leave or enter the zone. Again, another thing is not enough to have a firewall or packet filtering, but also we need to have rules that says, well, some traffic can go in and out, some is restricted. In the case of the example that I provided, well, only the traffic from this green host can go, but other traffic from other hosts is not. So now we have clear rules of how the traffic go between these two zones. The idea, according to the Canadian Centre of Cybersecurity, the idea of the physical versus the physical security zones versus the network security zones is the physical security zones that are created by the security agencies when there's maybe an event, right? So what they do in an event, whether it's political or a game or something or celebration, something that requires security. So what they do, they have multiple physical security parameters or zones. So, for example, the most restricted zone is in the middle, where only the guests and the VIPs and the participant they can enter this physical zone, right? So if there's a celebration, well, then only people who are participating in that celebration they will be in this zone, in the red zone. The and this will be the most restricted. The other or inclusive or outside of this zone, we have this orange zone, zone number 2, where maybe um, support staff, merchants, some maybe cleaning staff. These people will be allowed to come in, but they cannot go to the physical zone, right? And then finally, the outermost zone will be maybe people need to be checked first. That's the most relaxed zone in terms of security, but we filter people who, if, maybe the media or some people who are uh, can participate in the celebration, but they cannot go to the first and the second and third zone. So this is how physical security is done generally. And by the time you go to the physical zone number 3, you have to pass through 3 security checks, right? The first one, and the second one, and the third one. So you are subjected to 3 checks before you get in. With network security, you cannot do it this way often. So what you need, the main difference is you have multiple entry points. And while the physical security zones are overlapping, the network security zones are not overlapping. They cannot be overlapping. At least commonly they're not overlapping. So what you need to do is you have to make different zones, and you have to put controls, which are firewalls and other devices, in the entry points between one zone and the other. So again, according to the Canadian Cybersecurity, you have multiple types of security zones. Here is a list: public zone, public access zone, operation zone, restricted zone, highly restricted zone, restricted extranet zone, and special access zone. Right? Um, if you go through the documentation, each one of them has a definition and reason, and it was designed. This recommendation was designed for government agencies and those organizations who wish to follow the government recommendations. In our case, we'll just focus on the top four, because these are the most common ones. So what's the public zone? The public zone is considered any open network that is not under the control of the organization. Any network that's not under my control is considered public zone. It doesn't matter what it is. Commonly, it's the internet, right? But also can be the WAN. The WAN links, they go through a service provider. They are provided by other party, so they're not totally under my control. So we will consider them public networks or public zones, and as a result, we consider these public zones as the highest risk. Right. So, by the way, when you look at these, for each zone, you need to understand what is the characteristic of the zone, and what are the common examples of the zone. So these are the things that you need to focus on. Public access zone. So this is a little bit confusing in the terminology. There is a difference between the public zone and the public access zone, right? So the public access zone is the interface between the public zone and the other zones in the network, mainly the operation zone. So this is the interface. The most common one is the demilitarized zone, or the DMZ. But any interface, any zone that serves as interface between the two, we can consider it as a public access zone. Usually in the public access zone, we include services that are needed to be accessed from the outside, from the public zone. Right? So if I want to, um, if I have a network, let's say you have the internet here, you have a firewall or a gateway, if you want to make it more general, and I have my internal network, and I have servers and desktops. This one is my web server, right? Again, sorry about the handwriting. And this is the internet. Now the web server needs to be accessed from the outside, right? I mean, it can be accessed from the inside, but usually we put a web server for guests or for visitors to look at, people who want to know information about the organization. This poses a security risk. This line here, this traffic poses a security risk because if you are allowing traffic to come here, by a little bit of effort, somebody may come to another server here. So this is usually not a very good idea, right? So instead, we can create a demilitarized zone where we move the server from here, we move it here. So now the access will come from the outside to the demilitarized zone, and any access from the outside to N will be blocked, right? So this will be okay. Maybe I should draw it in green, and the rest is blocked, right? So DMZ is a common structure in networks. From the perspective of the Canadian cybersecurity recommendations, we will call this public access zone. Right? That's one example. Another example is any VPN. A VPN will allow us to get access from the outside to inside. The VPN will be the subject of the next lecture. So this is also an example of public access zone. All right, so we'll move on. Public access zones are considered somewhat risky, not as risky as the internet, but also not as secure and trusted as the LAN. So they are medium risk or somewhere in between. Again, the VPN, the termination point. The VPN itself is encrypted and is unlikely for someone to be able to get in the VPN itself. But the weakest point always the termination points, whether it's here or here. So these are the riskiest points. So at this point, maybe somebody is sitting with a remote, with a laptop, and initiating a connection using a VPN to the internal network. So the risk is with somebody who is maybe infiltrating this laptop at the top here and getting in, and also somebody who's coming out of this VPN and hacking the rest of the network. So these are the riskiest point. So what do I do about them? Make sure that they maybe terminate in a DMZ rather than the VPN terminating in the local network itself. So we'll talk about this in another lecture. Operation zone or zones, it could be more than one zone in the network. Operation zones is where most end systems or end user systems are located, traffically generally unrestricted within the zone, and it can originate either internally or from authorized external sources. Right? So what does that mean? Means in this particular example, we consider this operation zone, right? And the traffic between the host here can be unrestricted. We can also make a limited exceptions to traffic coming from here to here or vice versa, from the DMZ to inside. Why? Well, consider email server. Email server, first of all, it needs to be accessed from the outside. So it has to go through the firewall, but also it may need to be accessed from the inside as well. So there is reasons for interactions between the public access zone and the operation zone. Again, I said there could be multiple operation zones. So in this example, I may have operation zone, this considered operation zone. These are still a local network, still under my control, the camera network. Um, and still this is an inside network. So I may have two operation zone. They have different risk levels, but they are still, I cannot consider them public zones because they're not public. We are not considered in public access zone because they're not accessed by anybody from the outside. So they're still operation zone. They are still internal zones, but still there are two different operation zones with two different risks level. So we may have actually multiple operation zones. I can give you another example where I can have this is security cameras at the top, desktops at the bottom. I may have another network where I have IP phones. So this will be also another operation zone. So I may have multiple operation zone inside my network. Okay, so operation zone examples: security cameras, environmental sensors, internal LAN, wireless can be another operation zone. Guest wireless, I may separate the wireless that's used by employees from wireless that's used by guests, and each one of them will be different security levels, different risk levels, and different zone. So I may have multiple zones inside my network, right? And remember, each zone has to have a clear perimeter, restrictive boundaries, and a separate level of security, right? So it's not just I draw a circle around certain devices and say this is a zone. No, it has to have a clear perimeter and restrictive boundaries or restrictions in traffic in between. Finally, the restricted zone. In this case, according to the recommendation, this is where we put our most critical, business critical assets, right? So if I have application servers, database servers, this usually more sensitive information, this usually put it in the most restricted zone. And this should be the most trusted zone as well, right? Because it has the most security. So back to my example. So if I want to extend my example here, so let's draw, there's a lot of lines here, so let's clear some of the lines. Okay, so I may also have another network or another subnet where I have my database servers or my application servers or any mission critical servers. So now I have multiple zones. Notice that I put a one firewall, but that's not necessarily the case. So this will be the most restriction, maybe the most restrictive rules in access in and out. So maybe the security cameras have no business whatsoever accessing this database, so there is no access from the security cameras to the servers. Maybe phones also don't need to access the databases of employees, so there's no access from here to here. Desktops maybe have limited access to the server. So anyways, we can design our rules so that the restricted zone would be the most secure. Sometimes, as an example of restricted zone, is the where we put our network management systems. Right? If I want to do network management, network monitoring, I put it in the restricted zone. So I may also have multiple restricted zones as well, with different purposes. Right? So examples: network services and management. Includes servers and software tools that facilitate network management, log collectors, backup databases, Active Directory, authentication databases, and so on. right? In the public access zone, we may put DNS, for example, proxy servers. Proxy servers, remember, needs to be accessed from the outside, right? Any internet-facing servers, email, for example, it needs to be put in the public access zone. Okay, so now when we divide our network into zones, we have two types of traffic. The intra-zone traffic, so this is the traffic that goes within the zone itself, and the inter-zone traffic, that traffic that goes between the zones. So what about these? Right. So traditionally, um, traffic within the zone is considered okay. Any traffic can go anywhere, no restriction whatsoever. That's the traditional approach. But then we have this new concept of zero trust, which means there is no trust anywhere in the network, and we have to monitor every traffic, and we have to um, um, just keep an eye on, so to speak, on the traffic going. So let me give you an example of why there is such risk and why we don't trust uh, traffic anymore, even with this zero trust concept. So let's take a look at security cameras, for example, right? And if we look at the security cameras, we see that okay, there shouldn't be any traffic going between ideally security cameras don't talk to each other, right? Right. Phones, they don't talk to each other directly. The traffic, well, the phones may talk to each other directly, so I'm not going to use it as an example. But there is no good reason for a phone to talk to a security camera, and there is no reason for a security camera to talk to any other security camera. So generally speaking, I may ignore monitoring any traffic between security cameras and say, oh, well, these are okay. I mean, you don't have to worry about them. But the issue is, a hacker may replace a security camera with a laptop and start infiltrating and hacking into other systems. So sometimes it's beneficial to have systems that monitor the internal traffic and make sure that the monitor traffic is still adhere to certain rules, right? The internal traffic or the intra-zone traffic is, first of all, if I see one security camera goes to another security camera, should raise a red flag. If I see this traffic from the security camera is supposed to be, let's say, UDP, a certain ports, and all of a sudden I see telnet, right? This also raises a red flag. So, in the concept of zero trust, even intra-zone traffic must be monitored and make sure that it doesn't violate rules. So sensor cameras, again, sensors themselves then may not need to talk to each other. But if I see irregular traffic coming, HTTP traffic coming from an IP phone, why would HTTP traffic coming from an IP phone? So there must be something suspicious going on, right? Interzone traffic, that's obvious. I need to restrict it. So I can restrict it at the entry points or the boundaries by a firewall, which is the common way, or also I can restrict it by intrusion detection systems, uh, data loss protection systems, which we will talk about later. Um, we can implement this either using hardware or virtual machines or software applications. As I mentioned at the top of this lecture, firewalls can be implemented as a piece of software in a host. We didn't expand on that much because it's outside the network security issue, but it can be implemented as to restrict access to a server, for example, right? Um, and nowadays, with the virtualization everywhere, all of these technologies can be implemented as virtual machines as well. Direction of communication can be asymmetric. What does that mean? It means that in this particular case, in the security cameras, I may have traffic coming from the security cameras going to the monitor in this bottom host here, or a screen that shows the security cameras to a security guard. So traffic will be generally going from the cameras to the host. A very little traffic is going the opposite direction. Right? So what is the opposite direction? So maybe the security guards wants to move the camera, tilt it, or change the direction of the security camera. So it sends the command to the security camera to move. So these commands are short and don't have a lot of data in them. So the traffic is not symmetric. And also, maybe to move a camera, I need to send HTTP traffic, while traffic from the camera to the screen is UDP traffic. So the traffic may not be the same in all directions. And generally, traffic is more relaxed when it goes from a high trust zone to lower trust zone, while it's more restrictive in the other way around. So if I want to go from the operation zone, which has desktops, go to the internet, I may say, okay, all traffic can go, no problem. While if the traffic in the opposite direction from the untrusted public zone to the inside has to be more restrictive. Right? So in a network with a lot of zones, it may not be easy just to sit down and create a rule set for everything in one rule, in one firewall. I may need to implement multiple firewalls and multiple rules, or a firewall, and I add to the rule set that we talked about. I add interfaces, so make the rule set a lot easier to manage by restricting interfaces. So this is an example of interzone controls where I have the different colors represent different or same restrictions, same type of zone. So the management and the application are blue. These are the restrictive zones. So these are RZ both. The green is operation zone. The orange is public access zone, and the red is the public zone. And you can see here, for example, A means all traffic. All traffic from the management goes to management, so that's intra-zone traffic. From the office to, let's say, from the office to the management network, we need to put a firewall. From the IoT network to the management, we need to put a firewall and also maybe an intrusion detection system. So we can, I'm not going to go into details, but we can have a map like this that simplifies the creation of the rules. So now if I look at this particular example here between the office and management, I can design rules specifically to handle traffic between the office and management, and vice versa, the management to the office as well, right? So it depends on if the rows are the source and the columns are the destination. So I have a set of rules from the management to the office, network versus office to management. And also I can have no access whatsoever. So these blank cells means that I'm not allowing any traffic between. Right. Okay, so I promised to talk more about the demilitarized zone, or DMZ. We see it commonly used, common practice in every network. So it is a physical or logical network, so I can build it by putting a switch, particular switch, or I can just create it using a VLAN. Um, uh, the demilitarized zone, DMZ, as additional layer of security. If you go back to, I said that this is not a good example of a design, so I'm going to go back and emphasize that. So this is a bad example. It's good to explain the rule set here, but usually we don't put uh, anything that needs to be accessed from the outside the same subnet as the private LAN, because that uh, poses a huge security risk. Somebody is allowed to access the server using port 80, but they can just hack into the server and they go and hack other systems the inside. So we need to move these servers and put them in demilitarized zone, right? So that's the reason for the DMZ. Um, we can create a DMZ using single firewall architecture where you have a firewall here and the DMZ is branching out of the firewall using an interface in the firewall. Old firewalls, they come with two up to four interfaces. So the two interfaces, obviously, uh, the outside and the inside interfaces, but sometimes they come with four. So one of them can go to the DMZ, right? If that's not available, then you have to split the private VLAN into VLANs, multiple VLANs. Split the private LAN into multiple VLANs, and one of them will be used as DMZ. Anyways, both of them are considered single firewall architecture, and now I can have three interfaces, and I can design firewalls, uh, particular firewall rules, particularly to allow traffic from the internet to go to these servers if they need to be accessed from the outside, right? And also allow or restrict traffic, either prevent traffic at all from initiating from the DMZ to the internal network, or allow specific traffic for specific port and specific destinations. Right? The problem with the single firewall architecture is that if the firewall is compromised, then compromised by somebody is able to log in into the firewall itself, either internally from the outside or the outside, and then changing the rules to allow traffic. So now we have compromised firewall. For more secure architecture, we can have multiple firewalls. So the front end firewall will allow traffic from the internet to the DMZ, and then we have another firewall that restrict traffic from the DMZ to the private LAN, and then we have back-end firewall, like we call it back-end firewall. This is more restrictive, more secure, but also more expensive. So unless there is a good reason behind it, again, as I mentioned earlier in this lecture, there is always a risk assessment process that needs to be done. If the risk is high enough that justify the cost, then okay. If it's not high enough to justify the cost, then probably you don't need to go to the extra expense of two firewalls. Okay, so now, as I said earlier in this lecture, when you hear the term firewall in industry, usually they talk about a lot of things. They talk about an appliance that does a lot of things, right? And they call them different names. They call them unified threat management systems or next generation firewalls. In this particular course, when I say firewall, we are talking about packet filtering firewall, right? Packet filtering firewall that looks at layer 3 and layer 4 headers. So it's restricted to the IP layer and the transport layer. If we're talking about proxy, this means that it looks at the content as well. So we have to limit the definition of a firewall to just packet filters. In the industry, the term, and rarely you can find the firewall that does packet filtering only. I mean, probably you buy a router that does packet filtering only by using an access list. But most systems that you can buy right now, they come in as a collection of multiple services. So a unified threat management system is appliance that includes several technologies, including a traditional firewall, which is packet filter, whether it's static or stateful inspection. Usually it's stateful inspection because static packet filters are no longer useful. Anti-spam, it may be included. Um, Application filter, intrusion detection, virtual private VPNs also can be packaged into firewalls, and web filtering that look at the URL and block or allow based on where you're going, which website. Also, you can have spam filters. It's actually mentioned here, spam filters, but you can also have um, sandboxes. So you can have multiple of things um, that can be included in the same box, right? Next generation firewalls do the same thing. Here, the two slides make it look like they are different, but in reality, it's just a terminology. At some point, UTM systems were the hype. Everybody using it's a marketing term. Everybody using them. Now, the common name is next generation firewall. So in reality, both are the same. When you hear the term next generation firewall, means that a firewall that has more than just packet filtering. It has intrusion detection, it has SSL inspection, deep packet inspection, which means looking at the payload, malware detection, antivirus. It has a lot of things. Some people make a difference between UTM and next generation firewalls. So some people say, oh, there's a difference, but in the reality there are no differences, right? So both of them, they do the same thing. So the two terms are almost equally similar, right? Okay, so that concludes everything we need to talk about in firewalls. In other recording or in other lectures, I may do some examples of how you create rules for firewalls and also how to detect anomalies. So we'll leave that to another recording. Thank you for listening, and we'll meet in another lecture.